Hello and welcome dear viewers to the another topic on IVIVC. The topic will cover the BCS and IVIVC. How the biopharmaceutical classification system is related to IVIVC and how IVIVC is related to the BCS classification. See, IVIVC depends on the availability of the data, that is information regarding the in vitro dissolution and information regarding the in vivo response or in vivo drug absorption or plasma concentration. So once you understand the concept of BCS and IVIVC, then you will have good understanding of how these things are related to each other and how we can correlate the formulation with the drug substance of BCS 1, 2, 3 or 4 and to the IVIVC. So let's start with the video. See, BCS classification system involves the use of solubility data and permeability data, and based on that data this system classifies the drug substances or active pharmaceutical ingredients, you may say, into the categories of BCS 1, 2, 3 and 4. So BCS is a scientific system, or you can say it is a framework which classifies the drug substances based on the solubility in the medias of physiological pH range and the intestinal permeability. It also considers the dissolution rate or drug release. So BCS is nothing but a classification of the drug substances from the pharmaceutics point of view, and that considers the solubility and the permeability, and based on that the drug substances are classified. Now the solubility and permeability we will see. So high solubility means when you can say the drug substance is having high solubility or low solubility. So for that we will see the high solubility meaning. Whenever highest dose or highest strength is soluble in 250 ml or less of the aqueous media over the pH range of 1.0 to 7.5 at 37 degrees Celsius, that time you can say that the drug is having the high solubility. The pH range is 1.2 pH to 6.8 pH as per ICH and WHO, and it is 1 to 7.5 as per the US FDA. So the basic meaning of this definition is, if you have a formulation in 3 strengths, consider it as 100 mg, 200 mg and 300 mg, and 300 mg is the highest strength, so that 300 mg should be soluble in 250 ml or less of the media volume. If that 300 mg tablet is taken twice, that time it becomes 600 mg. So now that 600 mg should be soluble. Also, in some of the literature you can find that the highest dose, that means the dose of the formulation taken at once. For example, if the dose is indicated as 2 tablets of 300 mg at a time, that means the highest dose becomes 600 mg. So it is not the dose which is taken in a day, it is the dose taken at a time. Then coming to the permeability, when we can say that the drug is having high permeability, And if the drug is not having high permeability, then it will be classified into low permeability. Permeability is considered based on the absolute bioavailability or the mass balance. Now, what is absolute bioavailability? It is the actual bioavailability. Absolute means it is the actual bioavailability or the mass balance. If you take 100 mg and how much mg is getting permeated. So that is mass balance concept. High permeability can be concluded when the absolute bioavailability is more than or equal to 85%. If you give dose of 100 mg and if it gets absorbed as 90 mg or more than 85 mg or 85 mg, then you can say that the drug is having high solubility. And if you are not getting the drug absorbed above or equal to 85%, that time that drug is having the low permeability. Generally, BCS class 3 molecules and BCS class 4 molecules are having the low permeability, and that's why their bioavailability is less. High permeability can also be concluded if more than 85% of the administered dose is recovered in urine as unchanged, that is parent drug, or as the sum of the parent drug plus phase 1 oxidative and phase 2 conjugative metabolites. That means you can consider the parent drug and metabolite both, because after permeation some drugs get metabolized. So it is not necessary that you will always get the parent drug above 85% absorbed. Sometimes the drug will get absorbed and then it will get metabolized. That's why you can consider the metabolites also. Now BCS class 1, it is having high solubility and high permeability. So these type of molecules have less bioavailability problems. Examples are like a very common drug is paracetamol, it is BCS class 1, metoprolol and cyclophosphamide. Rapid or very rapid dissolution can be achieved by IR formulation design for the BCS class 1 drug. These drugs shows rapid absorption because these are highly permeable molecules. They are highly soluble and they are highly permeable. Then coming to the BCS class 2 molecules, they are having low solubility and high permeability. And because of the low solubility, the dissolution rate or drug release becomes the rate limiting step for absorption. If the drug is not available in solution form, it will not be available or it will not be available as absorbable form. Because whenever the formulation is given by oral route, for example say tablet or capsule, then that tablet or capsule disintegrates, and after disintegration the drug goes into the solution and then that dissolved form is getting absorbed into the systemic circulation. So that is the general thing what happens inside the GIT. And if the solution is not there, drug solution is not there, or drug is not available in the solution form, that time it will not be available for absorption. BCS classes are divided into BCS class drugs are divided into subclasses like 2A, 2B and 2C. These are based on the nature of the molecules, that is PK, acidic drugs, basic drugs and neutral drugs. So class 2A drugs are weak acid, ibuprofen, ketoprofen are the examples. Then BCS class 2B drugs, these are the basic drugs like carvedilol and ketoconazole. And BCS class 2C drugs, they don't have any PK and they are neutral molecules. Example is fenofibrate and danazole. Bioavailability of the BCS class 2 molecules depends on the drug release or dissolution rate and the formulation design. If your formulation is rapidly dissolving or very rapidly dissolving, or it is slowly releasing the drug over the pH range or over the pH profile or throughout the GI, you can say, if you consider the IVIVC, then dissolution rate is the limiting step, and that's why for BCS class 2 the IVIVC can be possible. Now also consider, if the dose of BCS class 2 drug is, let's say for example, it is 5 mg, 10 mg or 20 mg, then these molecules will not show very slow dissolution time because the dose is very small. But if the BCS class 2 drug is there and its dose is high, then you can get some release profile. The examples of BCS class 2 drugs are ketoconazole and carbamazepine. Now coming to the BCS class 3, these are the molecules or these are the drugs which have high solubility and the low permeability. And because of this, these molecules or drugs have limited drug absorption and have the limited bioavailability. Rapid or very rapid dissolution can be achieved by higher formulation design. And this is possible because these molecules have high solubility. Examples are atenolol, ranitidine and acyclovir. Then coming to the BCS class 4, these are the most critical type of drugs to formulate into oral formulations. If someone asks you the question that which BCS class drugs are difficult to formulate, then you can say BCS class 4, these are the most difficult, and then you come to BCS class 2, these are considered as critical. But if you work on the particle size or some formulation design, then you can easily formulate the formulation with BCS class 2. But BCS class 4 drugs are very difficult to formulate and to match in the bioequivalence studies. The reasons are these are with poor solubility and poor permeability. So you cannot predict their behavior in vivo based on the in vitro data. Poor drug absorption and bioavailability, limited by both solubility and permeability. Then low dissolution rate, and these are difficult to formulate for oral administration. Examples are ritonavir, furosemide and some of the anti-cancer molecules like Taxol derivatives. Now some dimensionless numbers are used in the BCS that we will see here. Those numbers are absorption number, dissolution number and the dose number. See, all these numbers are the dimensionless numbers used in the BCS classification, and these are the ratios or these are the some numbers which are calculated on the basis of the dissolution rate or absorption rate, then residence time and the solubility of the drug. So absorption number is the ratio of mean residence time and mean absorption time. That's why the permeability affects the absorption number. Then dissolution number denoted by Dn. It is the ratio of the mean residence time to the mean dissolution time, and dissolution affects the dose number. Then come to the dose number. D0, mass of the drug divided by volume uptake into saturation solubility. See here, the solubility affects the dose number. So these are the important terminologies. You can remember these things. Absorption is affected by the permeability. Then dissolution is affected by the residence time and the dissolution time, and the solubility affects the dose number. These are little bit critical to understand here, but you should know that These are the three type of dimensional less numbers used in the BCS classification. Now coming to these numbers and the BCS classes. So BCS class 1 have high absorption number due to high permeability, then higher dissolution number due to high solubility, and low dose number due to high solubility. If solubility goes down, dose number will go up. BCS class 2 drugs have high absorption number because of high permeability, lower dissolution number because of low solubility, and higher dose number because of low solubility. Then BCS class 3 drugs have lower absorption number because these have low permeability. Then higher dissolution number because of the high solubility. Lower dose number because of the high solubility. Then BCS class 4 drugs, these are the low solubility and low permeability drugs, and these parameters or these uh, properties makes the drug substances dependent on the drug substance properties. So the low solubility, low permeability makes the parameters dependent on the drug properties, and these are considered on case by case basis. BCS class 4 drugs may require the solubility enhancement techniques to improve the solubility and the dissolution rate. The absorption and bioavailability of these drugs are low. Now coming to the BCS class and the IVIVC possibility. So BCS class 1 drugs, these are highly soluble and highly permeable. So gastric emptying time becomes the rate limiting step, as the drugs can get rapidly absorbed once this drug solution enters into the intestine. Dissolution rate impacts the IVIVC. If the dissolution rate is rapid or very rapid, that means the complete release within 15 minutes or 30 minutes, then it can be said that the formulation behaves like solution. If you formulate the capsule or tablet formulation with BCS class 1, and if it is having a DT of around 5 minutes and the complete release within 10 minutes or 15 minutes, then once the formulation is taken by oral route, within 15 minutes or 30 minutes, it will go into the solution and the formulation will behave as a solution. That's why the gastric emptying time will become the rate limiting step, and not the dissolution will become the rate limiting step. For BCS class 1 drugs, that time gastric emptying will be affecting the IVIVC. The absorption happens from the intestine for most of the drugs, and thus for the rapidly dissolving dosage form, the gastric emptying time become the crucial rather than the dissolution rate. Because the dissolution is already there. Now the dose is dissolved into the gastric environment, and after the emptying into the intestine, it will get absorbed. If the dissolution rate is lower than the gastric emptying time, then the IVIVC can be possible. Now here one thing is important to consider, that if you give or if you make the formulation with the release profile for around 1 hour or 1.5 hour or 2 hours, and which is more than the gastric emptying time of, let's say, for around 20 to 30 minutes, then IVIVC can be possible. IVIVC possible for ER formulation with BCS class 1 drugs. So it is obvious that ER formulations will be with good IVIVC. You can predict the IVIVC for ER formulations. Now coming to the BCS class 2 drugs. For these two BCS class 2 drugs, dissolution rate will be the rate limiting step. BCS class 2 drugs are low soluble and high permeable, thus IVIVC possible when the in vitro dissolution and in vivo dissolution is similar. It can also be possible if the dissolution rate is longer than the GI emptying time. If the dose of the drug is very high, then the permeability also can affect the absorption of the dissolved drug, thus making IVIVC less possible. So consider here the dose affects the solubility and the dissolution rate. That's why for BCS class 2 drugs, dissolution rate is the limiting factor. Coming to the BCS class 3, these are having high solubility and low permeability. Thus, permeability is the critical factor for absorption. The permeability is the intrinsic property, so very less or no IVIVC is possible. Here I have shown a picture of people are standing for the gate to open. So consider these people as drug molecules and this gate as a permeability channel. So if the dissolved drug is available but this gate is not open, then the drug molecules will not permeate. So here the permeability will be the rate limiting step and that cannot be predicted. Then coming to the BCS class 4 drugs, these are low soluble and low permeable, thus the solubility and absorption depend on the drug molecule. If you take example of 2-3 BCS class 4 molecules, these all will have different solubility rate and different dissolution rate and different permeability and different bioavailability. These will be on case by case basis. Some of the BCS class 4 drugs can be made soluble or their dissolution rate can be improved by just milling or mixing with some ingredients or mixing or using the surfactants or wetting agents, while some other may require the technologies like spray drying or hot melt extrusion to make the solid dispersion, and then these will get dissolved or these will get solubilized. So these are the molecules which are very critical to formulate, and generally the dissolution enhancement technologies are used for this type of molecules. Dissolution depends on the CMS of the drug substance and the critical material affects the possibility for IVIVC. Examples are API PSD, API polymorphic form or salt form, then polymer level if solid dispersion is there, or surfactant level concentration. These are the critical type of materials or critical CMAs and CPPs which affects the dissolution rate, and for BCS class 4 molecules IVIVC is least possible. Then coming to some terms or some important things which are required to be considered for whenever you are going for IVIVC. In vitro solubility and in vivo solubility of the drug substance. If you get in vitro solubility, so it is not necessary that the same solubility will be achieved in vivo. Then disintegration in vitro and disintegration in vivo, because in vivo environment is very difficult to achieve in the in vitro testing. Then in vitro dissolution and in vivo dissolution. We can collect the data for in vitro dissolution, but we don't know what is going to happen inside the body. Then precipitation in the GI tract. Some APIs get precipitated at some specific pH when they enter the GI environment. Like first of all, the formulation or drug exposed to the acidic pH of stomach, then to the 4.5 pH around or 5 pH around into the duodenum, and then it will reach to the 6.8 pH. So from acidic to less acidic or neutral, and then it will reach to around basic pH. So there are chances of precipitation, and once that precipitation happens, the drug becomes insoluble. So that insoluble particles or precipitate once again can dissolve, and this can happen sometimes. So these things are not under the control or cannot be predicted by in vitro dissolution testing. Sometimes the sequential dissolution testing is done to predict these things, in which the pH of the dissolution medium is changed to study the effect of change in pH onto the precipitation. Another important thing is degradation of the drug molecules inside the GI environment. If the drug is getting degraded, then it is difficult to understand the logic or the science behind the IVIVC for these type of molecules. The examples of these molecules are the molecules which are made or formulated in the form of enteric formulations, like esomeprazole is there, ranitidine is there, rabeprazole is there, and omeprazole is there. So these are the molecules which get degraded. So we cannot understand, or it is very difficult to understand that which formulation is releasing the API at which site and how much of the dose is getting degraded. So for these type of formulations, or the formulations containing the drug substances which are sensitive to pH, or the drug substances which get degraded into the GI environment, for those type of formulations it becomes very critical to have proper IVIVs. Then the dissolution and precipitation and degradation may affect the parameters like Cmax, Tmax and AUC. So without having proper data from some of the B study batches or clinical study batches or bioequivalence batches, it becomes very difficult to have proper IVIVC. So this is regarding the IVIVC. Always consider your formulation, the BCS class of the API and the disintegration properties to have proper IVIVC. See, generally the IVIVC is asked in the interviews to understand whether the candidate know about these things and whether the candidate is aware about the IVIVC and BCS terminology. Keep on watching the videos from Pharma Learning in Depth channel. Kindly do like, share and subscribe. Also share with your colleagues and friends so that they can get the knowledge for these videos and they also can learn these things. Thank you for watching.